From this lecture onwards, I will start discussion on plane groups. So, a plane group is basically a combination of a 2D lattice with a 2D point group. So, now we have 5 2D lattices and we have developed 10 point groups. But not all point groups can be added to any particular lattice. It will be determined by the symmetry of that particular lattice. So, first let me list down the 2D lattices. So, we have primitive oblique, primitive rectangular, centered rectangular, primitive square, and finally, the fifth one, primitive hexagonal. So, all these lattices were developed on the basis of some required necessary symmetry that they must have. For example, primitive oblique can have a one-fold or a two-fold rotational symmetry. A primitive rectangular at the very minimum should have a mirror symmetry. A centered rectangular, the same thing, mirror symmetry. Primitive square should have a minimum four-fold rotational symmetry, and primitive hexagonal can have either a three-fold or a six-fold rotational symmetry. So, based on that, the point groups that we can add to each of these lattices. So, point group 1 and point group 2 can be put in the primitive oblique. Primitive rectangular, one can put M, in fact both of them, primitive rectangular as well as primitive centered rectangular. One can add mirror or M point group or the 2MM point group, because two-fold rotational symmetry would also fit in the rectangular lattice. Coming to primitive square, clearly it should have a point group 4 or it can take point group 4 MM. And then the primitive hexagonal, as I had said, minimum it requires a three-fold or a six-fold rotational symmetry. Therefore, all the point groups having three-fold and a six-fold can be accommodated by primitive hexagonal. So, point group 3, point group 3M, point group 6, point group 6 MM. Now, let us take an example just to see why I am saying that only these point groups or the specific point groups for a specific lattice have to be, you can say, compatible. So, these are what I can call compatible point groups for the individual lattices. So, let us take an example. So, let us consider a square lattice. So, let me first draw some lattice points. So, let us say that this is a square lattice. So, it will have four-fold symmetry. Anyway, in the lattice without adding any motif, the lattice will have the maximum possible symmetry. So, it also has lots of mirror planes as well. Let us take a particular motif. So, the motif that I am taking is, let us say these are atoms. There are two kinds of atoms. There are big atoms and small atoms. If I look at what kind of point group this motif has, well, it has a fourfold right in the center of the larger atom, and it has mirrors running. In fact, these are not the only mirrors, it will have mirrors running like this as well. So, this is the kind of point group. In fact, this point group would be 4 mm. And as I am suggesting that this 4 mm point group would be compatible with the square lattice. So, let me put this motif now at every lattice point by putting the larger atom center coinciding with the lattice point. So, I have decorated all the lattice points with this particular motif. Now, if I look at it, this structure that is created or this pattern that is created has fourfold at every lattice point. And it will also have several mirrors. And also these diagonal mirrors and so on, and it has even lot more symmetry than what I have put in this particular pattern. So, this is fine that the symmetry of the lattice has been preserved. There is a mirror plane existing there, which is the minimum requirement. It has lot more symmetry. Now, consider the same square lattice in a second example where I have a different motif. So, this is roughly a square lattice that I have drawn, and let us take now a different motif. The motif that I am taking, so there is still a larger atom, and instead of 4 now I have 3 small atoms. If I look at the point group of this motif, clearly it has a threefold symmetry at the center of the larger atom, and it has these 3 mirror planes as well, and therefore, the motif is 3M. At 3M I have not listed as a point group to be put in the square lattice. Let us see what happens. Anyway, let me put this motif. Okay, so I have put this motif at the each lattice point. Now, let us see, is there a fourfold rotational symmetry present there? If you look at it carefully, you will find that the fourfold is, this pattern no longer has a fourfold. Now, let us see whether it has a threefold. After all, we started with the motif with a threefold. If you look at it carefully, even the threefold is not there. In fact, if you look at it carefully, you will find that in fact there is no rotational symmetry at all, or you can say it has one-fold rotational symmetry. So, what is the any other symmetry present? Yes, there is. There is a set of mirror planes that are present, and these are these horizontal mirrors. and of course, there will also be mirrors here. So, now what kind of a pattern it is, or let me put it this way, that what kind of a lattice it is. We will see that we can no longer call it a square lattice because it does not have a fourfold rotational symmetry. This is right from the beginning of this course. I have been repeating this again and again, that the lattice type is decided by the symmetry, and therefore, so which lattice it should be. If you look at it, which lattice requires a minimum symmetry of a mirror plane, and we will see that you will find that it is primitive rectangular or centered rectangular. Now, this is not a centered cell. I can, if I want to define a unit cell, a conventional unit cell would be, I can define out here. So, this is a primitive cell with lattice points at the corners. So, it is primitive, and I said that it should belong to the rectangular crystal system, and therefore, I say that this is a primitive rectangular lattice. So, the lattice of this pattern is primitive rectangular and not a primitive square. Even though the unit cell that I have defined, and if I look at the lattice parameters A and B, we will find that in the specific case A is equal to B, but that is not how you define a lattice. So, this is just a coincidental equality. So, I hope this makes it clear that why certain point groups have to be attached with certain unit cells or certain lattices. So, with this in mind, now we start looking at how to develop the plane groups, but before we can do that, we have to kind of now look at how point symmetries combine with translation symmetry, because once you put it in the lattice, it will have a lattice translations would be involved, and we will be talking about now combination of translations with point symmetries. So, let me go back to last lecture where I had posed this particular question here, that I have two mirrors which are parallel mirrors, which are spaced, or the distance between the mirrors is a. So, let me just draw this once more. So, this is the question: mirror M1, mirror M2, the distance between them is a, and now we want to find out what is the reflection operation sigma 1 followed by the reflection operation sigma 2, what symmetry operation it should give me. So, let us start with a asymmetric motif. The reflection operation by mirror 1 will reflect this asymmetric motif out here. So, this is motif 1 right handed to motif 2, let us say left handed, and motif 2 gets reflected by mirror 2 through the sigma 2 reflection operation. Let us say that the first motif has a distance of delta from M1. The reflection to the motif number 2 would also be at a distance of delta on the other side of the mirror. Then let us figure out some more lengths here. Motif 1 is at a distance from mirror 2 by a distance of a minus delta. And let me just also say that I am measuring this distance of the motif from one particular point on the motif. So, now where will when I reflect motif number 2 by mirror 2, where will this go? So, the total distance that motif number 2 has from mirror 2 would be delta plus A minus delta, giving me A plus delta. So, therefore, mirror 2 will reflect this motif number 2 to the other side of the mirror by the same distance. So, therefore, I can mark out a similar distance A plus delta, and this is where the motif should come at this distance. This is now motif number 3 and it has become right handed. If I look at motif 1 will also be reflected by mirror 2. Now, this motif 1 is at a distance of A minus delta. Therefore, this motif would perhaps come somewhere here and with the handedness changed, which is 4 left handed. So, this distance, if we look at, would be A minus delta. So, now how does, if I look at, I went from motif 1 to motif 2. So, this was through a reflection operation sigma 1, motif 2 to motif 3 was through a reflection operation sigma 2. Now, I want to go from 1 to 3. How can I do that? So, first of all, motif 1 was right handed, motif number 2 was left handed, motif number 3 became right handed again. Handedness is the same for motif 1 and motif 3. So, therefore, the only operation that can take me from 1 to 3 is a translation operation or through a translation vector t. Now, what would be the magnitude of this translation? So, the magnitude of this translation is clearly delta plus A minus delta plus A plus delta, and we will see that all the deltas will cancel out and we are left with 2A. So, therefore, clearly I have a translation operation T bar whose magnitude is 2A. So, therefore, sigma 1 followed by sigma 2, the symmetry operation that I get is T bar, the translation operation, magnitude being double the spacing between the two mirrors. Now, we will also, if you will notice that of course, there would also be a mirror that will come here, and this mirror is basically being translated by this particular translation. Okay. Now, conversely, if I had a mirror and a translation T, of course, this translation will take this mirror here as well, but what I have essentially is reflection followed by translation. So, the new symmetry operation that should come is a mirror plane in the middle of these two mirrors. I can denote it as M prime. So, this is just the converse of the previous situation. So, if this distance was A, then this distance would be A by 2. So, therefore, I get reflection operation of sigma prime located at A by 2. Now, this is not the only way I can combine a translation with a mirror. I can also combine a translation with a mirror, where the translation is at some angle with respect to the mirror's normal, you can say. So, I have translation, mirror. So, in this case also there would be some symmetry operation that may come about. And let me also make it clear that these translations are lattice translations. For now, I am not going to solve this particular problem, but it simply said that I will simply state that this leads to a new symmetry operation called glide. So, this is not yet discussed. So, we will be discussing this later. So, we will discuss this in a later lecture. So, this brings us to the close of the lecture. In the next lecture, I will start out by talking about, just like we did rotation and reflection matrices, we will also develop a translation matrix as well. So, that I can combine translation with other point symmetries to by multiplying matrices to obtain the third operation. Thank you.